Hello everyone. Today we're gonna solve the work break problem. This problem is an upgraded version of the implement trial data structure, the prefix tree data structure. If you haven't seen this video yet, I will leave it at the end of this video on the right side so that you can have a look on it first. And I highly recommend you to watch this video before coming to this video. So this problem asks us to see whether or not we can break a string using a dictionary of these words. So basically, we can separate this string into two parts so that these two parts are the words in the dictionary right here. So for this problem, we can also do that by split this one, apple, pen, and apple. But for the last one, we can not do that because we don't have a way to break this word into by using this word in the dictionary. So how can we do that? So first of all, I will use a little bit of dynamic programming right here. Let's say if a string uh, s0 to I can be can be break broken by using the word from a dictionary, I will call this one is I will use a can break 0 to I, right? So I will call the can break I will be equal to 2, which means that we can break this string using the word in dictionary. So for example, if we have this one, right? So which means that I will have a can break. Can break array will be equal to 0, 0, 0, 1 because we have the word lit in this dictionary, right? Yep. With this dictionary, we will have this one is 1 and 0, 0, 0, 1 because we can break this string using this one. Yep. And this is a little bit of dynamic programming right here, but not too much. And then how can I check whether or not I can break this one into uh, using this kind of string in a dictionary? So what I'm gonna do is that for each of the length, for example, I will start from I right here and from J right here, and I will check whether or not the string from Si to J is in our trie data structure or not. So if we can check whether or not we can find this one, and we already have the can break of I minus 1 and can break of I minus 1 is 2. That means that we can update can break of J will be equal to 2 as well because we already have this one in dictionary and we just need to connect with the previous one. So that's basically the idea. And then finally, we can check whether or not the final position, the can break of S, the length of S minus 1 is true. If it's true, we can break this string, and if it's false, we cannot break this string. So that's basically the idea. And how can we do that? So first of all, we're gonna have a trie right here, and then we're gonna look through each of the string, right, and insert it into our dictionary. So step one gonna be let's put it right here. Step one gonna be insert all the words in dictionary into our try, and the step two gonna be for each segment, for a substring, ij, we check if we can see si to j in our try or not, and if yes, we're gonna update can break of j. So that's basically the idea. So first of all, we're gonna look through all of the words in our dictionary. Um, yeah, let's say just dictionary. It's gonna be easier for us. And then we have to insert it into our try. And I'm gonna have a bool vector of can break. We're gonna have let's say we get the sign of s first, and then we have n plus one element with four. All of them are false, and we have can break at 0 gonna be 2, because if we don't have any letter, the s is an empty string, and we just not gonna do anything and just return 4 right here. So for I equals 0 and I less than n, so we're gonna look through each of the position in the string f, and we have the current string to get the substring would be equal to this. And then if we have the can break, I is 4, we're not gonna do anything because uh, even though if we can break, we can see the substring from I to J, we cannot use it to break the string S. So all we need to do is just skip this. Oops. Uh, Continue. And then we're gonna look J from I and J less than N. And to get all the substring, um, let's say this is the current substring. The current substring we're gonna have to update with sj. And if we can search for this word, uh, current substring, we're gonna update can break of j plus 1 would be equal to 2. So that's basically the idea. And then we're gonna return the can break and right here. So that's all the idea for this. And the time complexity gonna be O n square, and the space complexity actually it's O n square multiplied by uh, the length of s as well, because we're gonna search for each word in our try, and the space complexity gonna be O of number of letter in our dictionary. So and the topic for this approach gonna be a little bit of dynamic programming and prefix tree, of course, all our try data structure, and string, of course. And yeah, I think that's all for this approach. And the next thing we're gonna do is that we have to implement the struct trie right here. Have struct trie, and we have a struct trie node right here. So again, if you haven't seen my video in the implement prefix tree problem, you should see it before we deep dive into this part. First of all, we're gonna have the max digit would be equal to 26 because we just have the lowercase English letters. Yeah, I guess yes, that's correct. So first of all, for the try node, we're gonna have is in word, and we're gonna have the next node gonna be the max digit. And for the try node, we're gonna have a root right here, and we have a constructor which is try node new, right? And then we're gonna have a insert function, and we're gonna have a search word function, right? Do we need to use different? Yeah, I think that's fine. No need to do it. So for the insert one, first of all, we're gonna have to look through all of the word, and we start with the root node, right? And for each of the character in the word nodes, we're gonna see if we already have the current part. If we don't have, we need to create, right? And if we already have, we just need to move the current node would be equal to the next node C right here. And if we haven't have it, we have to create the next node C. And finally, we're gonna mark the flag is n word right here gonna be equal to 2. Is yeah, that's basically the idea for the search function. And for the insert function and for the search, we're gonna have to uh, travel. First of all, we get the root node and we travel through all of the character, and we do the same thing right here. If we already have the path, we're gonna move to the next one, and if we don't have the path, we will just return false because we will not find any word. We will not find any word in our dictionary with this word. So finally, we will return the current is n word right here. Yes, that's basically the idea. Let's see how it goes. Math digit. Oh, we haven't have this function yet. And this function as well. Hmm. First, we're gonna convert from A to Z. This one we convert A to Z to uh, 0 to 25. So we just need to get C minus with A, and we return max of the digit. And we're gonna do the same thing right here. But first of all, we need to create a new node first. Next digits. This one, we have bool can break with. Oh, this one is vector. A vector, right? Sounds good. Perfect. And I think that's all for this question with the prefix tree data structure. And if we analyze this problem a little bit, like deeper, we're gonna see that uh, all we need to do is check whether or not this string this substring is appear in our dictionary. So we also can use a hash map to do it, or basically we can just use a set to store all of the substring in dictionary. And finally, for each of the substring, we just need to check whether or not this substring is uh, in our hash map or not. So let's say this one is the first approach. We're gonna use the prefix p or the trie data structure, and the second one gonna be pretty much the same thing. The second one gonna be using just the hash map, the hash table approach, or for or in our C plus plus we're gonna have just the an or the set string. Yep. Or we can use another match as well. It doesn't matter. Just an key value that structure gonna be fine. So how can we do that? We're gonna keep everything the same thing here. Not much as of a difference. So first of all, we're gonna need to insert all of the word into our hash table. Just basically the same thing here. So to insert all of the word, we just need to look through all of them in our dictionary, and then we're gonna have a hash table. Uh, is it the is it need to break or I? Yeah, we need to break it. That makes sense. We have the hash table dot insert the word for the first one, and we're gonna do the same thing right here. We just need to adjust this search function to uh, to search in our hash table. We just need to adjust that. If we can see the hash table, we can find the current substring. Right. If we can find it, that means that we can assign the can break j going to be equal to. So this one if is different with the n, which means that we find it in our hash map. We're gonna just can break. We can just update can break of j gonna be equal to Yeah, very simple, right? So basically, we're gonna replace the prefix tree by using hash map or hash table approach. And the time complexity right now gonna reduce from because we already insert all the word to this, so the time complexity gonna be O of uh, each of the word in dictionary multiply with n is n is this. I think it's gonna be the length of dictionary as well, and we're gonna get the max. Which one is dominant? We're gonna get the max of this one and n squared right here. Because for the looking up operation is gonna take O1 right here. So we basically the time complexity for this one is O n square instead of n square multiplied with s like we did for the prefixum. So this one have a better time complexity. Okay, let's see how it goes. All right, that's all for this question. And if you have any question, just leave it below and I will answer all of them. Thank you.